old friend of mine. Not quite as old as I am. We've known each other since the 1960s, basically late 1960s. Leonid Grishchuk grew up in Moscow. And I met him when I first went to Moscow in the late 1960s. We've been very close friends ever since. He was the first person many, many years ago to point out that gravitational waves can be amplified by inflation. That was before inflation was invented, but can be amplified by the expansion of the universe. He is a person who loves to pick fights. He's picking fights today with LIGO. He has a different way of thinking about things sometimes, and he sees things that other people miss. Let me say, he and I have been fighting about this particular topic in recent days. And just a preview to give your attention, I think by and large, but perhaps not entirely, he has won this battle. And so I recommend you pay some attention.
Thank you very much, Kip. Kip is a very old friend, it is true, but he is also my hero. And what does it mean to somebody is a hero? You're gauging your behavior and you're asking yourself, would Kip do this thing? And I'm thinking, no, it is too silly. Kip would not do this. So you are normally doing another silly thing. You are doing different silly thing. So I'm always asking myself what Kip would do. Indeed, I think that there is something to discuss. Kip advertised in another room that LIGO-associated people should come because Grishchuk will say that everything what you are doing is wrong. It is not quite this way, but I really think that in this area there are two sides of this phenomena. I think that one is some general physics. You know, it is interesting to see gravitational waves in the context of all other things that we are doing, electromagnetism and so on. And another is applications, how important it is for whatever we are doing. So let me first go quickly through the content. So for me, originally, this electromagnetic physics was very important. I was wondering, how could it be that gravitational waves are less rich than electromagnetic waves? We know that electromagnetic waves are moving particles in the wavefront, but also back and forth in the direction of propagation. And everywhere you see that people are telling you that gravitational waves are moving test particles in the wavefront. It cannot be true. So therefore, I started from this electromagnetic analogy, and I think that you will see that indeed in this aspect, in the motion of particles in the field of gravitational waves, there is something what we are tempted to call a magnetic component. Whether it is the right word or not, I don't know. Kip does not like it. So probably I should say first order corrections in L over lambda or whatever. However, I think that there is some association with magnetic components. So we will start from this electromagnetic part, then it will be kind of theory of this effect by itself. So of course we will go to plane gravitational waves in the inertial Lorentz frame, because we will be comparing with electromagnetic waves. Electromagnetic waves at a global Lorentz frame, and this is what we normally do. The best what we can do here, it is local inertial frame. So we will better understand by going through in a local frame. We will consider how free masses are moving, and of course our emphasis will be on magnetic components. We will see that indeed they can be classified as a ratio of size of your distance between the particles, if you like, test particles before the arrival of gravitational wave and wavelengths. So typically it is a small number, but it is still, in our realistic condition, will be something like 10%. It is important to derive these equations from various perspectives, because you better see the phenomenon. So sometimes we are deriving from geodesic deviation equation, because it is kind of immediately Newtonian form of writing. It is product of mass time to second derivative is equal to the force. So where this force is on the right-hand side, normally we write simply curvature tensor, but now we will see that there are higher derivatives of curvature tensor, and this is what makes in the geodesic deviation equation this force, which I call magnetic force. What is important that these components of motion, they modify not only the general pattern of motion of a test of particles. So we will have complete description. So there is a set of particles in a rigid box, and we will know everything, how they move. But for us, what will be most important that it makes variations in distance between test masses. So it is not only this electric, but also magnetic component. Is it me or somebody else? Or they already...
People on the phone, please mute.
Or they already disagree. Do you already disagree with me?
Oh, they want to know what slide number you're on?
It's the first one where it says content.
Okay. Then we will come really to possibly center of attention for most of people here in the room. It is how a two-arm interferometer responds to incoming plane gravitational wave, and we will take into account this magnetic component. So it will lead to, so to say, magnetic modifications in the angular frequency and polarization dependence of gravitational waves. And therefore, strictly speaking, what we were doing before was wrong. I mean, to the extent that you always should do better. The astrophysical example will show us the size of these magnetic contributions and where we can possibly make errors. I believe that accurate astrophysics is impossible if you do not take into account all these effects. But of course, it depends on your understanding of accuracy. If you are happy with errors of 10, 15%, then of course, probably it will not affect your life. And finally, I actually urging you to take this seriously into account in the data analysis pipelines. So let's, you were teaching your students, you know this perfectly well, but simply let us remind what is going on in the field of electromagnetic waves. So electromagnetic wave is coming from X3 direction, and depending whether it is linearly polarized or circularly polarized, what is happening? Electric field is driving particle this direction, because electric field in this plot is oriented along x1. Then it generates velocity of the particle, and then velocity of the particle multiplies by vectorial product with magnetic part of the field, and it produces the force and motion in this direction. So actual trajectory, it is number 8, and clearly there is x3 component of displacement, which is back and forth of wave propagation. It is only in the exceptional case of circularly polarized electromagnetic waves that the charge will move in the circle without x3 displacement. So in the field of electromagnetic wave, let's try to develop some intuition. This amplitude x1 is small in comparison with wavelengths of electromagnetic wave, and it is called the weakness. It is parameter characterizing whether the electromagnetic field is strong or weak. If it is comparable, it is a strong electromagnetic wave. It will drive electron to the velocities comparable with velocity of light, and this size will be comparable with lambda. In our case, we are considering weak electromagnetic waves, weak gravitational waves. Therefore, x1 is small in comparison with lambda, but x3 amplitude in this direction even smaller. You take this x1 and multiply to extra small ratio, which is x1 over lambda. So we kind of try to feel that something similar is going to happen in the case of gravitational wave. What we normally do, of course, we are taking synchronous coordinates. We are removing everything what is not necessary. We are writing two polarization tensors. So if there is a wave vector, then M and N, two orthogonal vectors, and you are forming two polarization tensors. You have two functions of time and x3 for a plane wave, and generally speaking, you have two different phases, but you can always use this remaining freedom in plane x1, x2 to make them equal and up to p over 2, and therefore we will be working with this form of expression for a plane gravitational wave. I call it, or maybe other people call it, is framed based on principal axis. So two linear polarizations, it is either this or this is equal to 0. Two circular polarizations, they are equal to each other or up to the sign. And now comes an interesting exercise. We cannot introduce the global inertial frame, but we can introduce at least the local inertial frame. What is the definition of this? We are going along the time like geodesic, and we want metric to be like Minkowski metric, and first derivatives, all first derivatives to vanish. It turns out that you will have to write this transformation. It is essentially an expansion in terms of this axis. x1, it is quadratic terms. In principle, you could write cubic terms, but they will not help you. You have reached all your requirements by this transformation, but you cannot drop. You cannot say, oh, I will limit myself, for instance, by this part. It is not local inertial frame, because if you do this, you have still did not satisfy the requirements of all derivatives be equal to 0 and metric being Minkowskian. So what I'm saying here is that we cannot proceed, we cannot do anything without quadratic terms, but there is no need for higher order terms. You can define your coordinate system as exact transformation, and it will be satisfactory. Maximum what we can do in local sense. So what is a nearby free particle? It is original synchronous coordinate, so every particle which has constant axis is riding on a time like geodesic, so it is nearby free particle. And therefore, to learn how this particle moves in your bar coordinates, you simply put here the values of positions of this particle. Of course, these derivatives are taken along the central line, so you know everything. And as a result, you will find that x1 of t, x2 of t, and x3 of t are given by this formula. So effectively, this is a crucial point, because at this level we understand that if there is no gravitational waves, of course, nearby particle is in a fixed position. If we are including what we normally do, zero order terms in ratio L over lambda, or infinite wavelengths approximation, putting k wave vector, wave number to 0, then we will come to something what we normally write. We normally write this line, and we normally say that x3 is a constant, so there is no displacement along the x3 coordinate. But now there are extra terms, they are proportional to k as indication of smallness, and we have to take them into account. So what we are teaching our students, we are showing them this ring of particles, and we are telling them that it will be shrinking this way, squeezing this way, so for a linearly polarized way, and after half a period, for a disk of particles, for us, it will be important to consider a disk of particles rather than simply a ring, because if you now take into account these magnetic terms, it turns out the disk itself is deforming. All these particles move up and down along x3, so accurate representation of the motion of particles is given by this figure, by this plot. Individual particles will make their own trajectories, which we do not discuss at the moment. But it is seen from this plot that actually the full picture should include deformations. It is kind of a saddle point. In reality, this point will be a saddle point because it is bending in orthogonal directions. So now there is a little bit of technical derivation. I'm not planning to go necessarily through all these formulas, but it is useful to know that it can be derived, and it gives you a fully consistent picture. So what people normally do when they derive equations of motion from the geodesic deviation equation, we introduce two-parameter family of time-like geodesics, and we introduce vectors which are tangent to each geodesic line and displacement vector by differentiating this function by d tau or by dr. So our central geodesic is at r equal to 0, nearby geodesic at some r equal to r0. So we are expanding this function. We are retaining only terms of linear in this small r0. We come to the geodesic deviation equation. We open big books, and we are discovering this there. So it is correct. It is correct. So second order covariant derivative along the word line is given by this expression, and what we normally do then, we specify to the local inertial frame, which makes it even simpler, and which makes our equation look like equation product of mass time acceleration is equal to force. However, it is only the first order approximation to the geodesic deviation equation. You have to take into account second order terms in your this separation parameter. You have to generalize the geodesic deviation equation, and it will turn out that in addition to this term, you have terms which are containing derivatives of curvature tensor, and also a product of curvature time with derivative of your separation vector. So now it is more difficult time of comparing these terms and making use of them. So in the local inertial frame, all these Christoffel symbols vanish. So on the left-hand side, clearly there is something like acceleration. On the right-hand side, there is something what we normally write. And there are extra terms. And we will have to figure out which of these terms are more important. Actually, from this line, you see that what will be important for us, it is this term rather than this one, because here you have extra differentiation. You are making lambda in denominator and separation, extra separation in numerator, L over lambda. This is how it appears. But there you have kind of velocity, which itself effect of first order in h, in amplitude of gravitational wave. So you have one h here, you have one h there, it is h squared. Somebody calls it magnetic term. I say, well, maybe for you it is magnetic term. This is what you expected. I did not expect this. I expected this. It is much more important because it is extra 10 to the minus 20. You know, I do not want to work with extra factor of 10 to the minus 20 or 25. So this term is much more important. Specifically in the field of a plane gravitational wave, when this separation vector is constant plus psi, then you have this line which you find in every textbook, but also you have this line which is magnetic force. It is electric force and it is magnetic force. It is proportional to velocity, if you like.
It's not magnetic force.
It is a magnetic force.
First order correction. Has nothing to do with
Yeah, Kip was, yes, because you were all educated in a wrong scientific school, you know? You were wrong educated. You were educated in the school, in particular in this context, that magnetic terms, it is different components of curvature tensor with spatial, or something multiplied with velocity, making the h squared. I was educated in Landau-Zildovich school. They were saying, look in the core of the things. It's simple matters. If it looks for you as a kind of a magnetic force, don't be afraid to call it a magnetic force. Anyway, Kip is right. I will not insist on saying that it is a magnetic force. But the fact is that your geodesic deviation equation will accept this form. It is product of mass times the acceleration. This is what we already know. This is what extra terms. Clearly, they have extra omega L parameter, and therefore it is smaller, KL term. And you can even show that it can be written in the form which is proportional to velocity, so I'm kind of still defending my desire to call it a magnetic force. What is more important that if you now solve, it is dynamical equations. We derived everything already by simply transforming from synchronous coordinates to local inertial frame. We already know everything, but it is very satisfying, of course, that when you now solve second-order differential equation, which is supposed to be solved in order to find these trajectories, you will come exactly to the same result. So whether it is magnetic or not, whatever you call, if you do correctly geodesic deviation expansion, and if you solve the corresponding equation of motion, you will come exactly to what we have already discussed. Now, it is something what I have already mentioned. It is the comparison of these two terms. This term was retained. It is linear in h. It is smaller in another parameter, r over lambda. But this term, for gravitational waves, it is quadratic because h here, h there. For other people who are studying, rotation of a pendulum or top in a gravitational field, where you have this term initially large. It could be arbitrary term. It is a particle's velocity of neighboring particle. It could be going with significant velocity, and therefore it will not be proportional to h, and therefore this term will be first order in h, and for some other applications you can justify that this term is more important, and you can call it gravitomagnetism. For us, we do not need this because we know which term is more important. Now we are coming to the variation of the distance. In a local inertial frame, now it is an elementary exercise because you know that your metric is Minkowski metric up to quadratic terms in this small ratio, and we are interested only in the linear terms, so we simply calculate these distances as we would do in laboratory. We are inserting all this already calculated x1, x2, x3. You take square root of x1 square plus x2 square plus x3 square, and you derive the new expression for the distance between two particles. And of course, it depends on location of neighboring particles. So L1, L2, and L3 show you where the neighboring particle is located. All that we have done in this approach of local inertial frame. Of course, you can do independently on frame if you define the distance as time, half of a time which takes for a photon to go to a mirror to return back, times velocity of light. It is your definition. By the way, this definition will give you a different result from a different definition. If you define the distance as a length of space-like geodesic joining these two particles, you will get what you want in approximations that we discuss, but in second approximations, they will be different. However, if you define this distance on the time difference, then you can derive exact formula, and I believe this kind of formula are used in LISA applications and so on. And if you take expansion of this formula, you again come exactly to the results that we have discussed before. So now we are really coming to the Practical applications.
Stop.
Okay.
Say, so the analysis that Leonid describes in terms of local inertial frames is kind of complicated. It's much simpler to take the standard Lisa transfer function, which is what he just referred to, and expand it in powers of L over lambda, and you get the same result.
Yes, Jan, in fact,
Walker.
after I saw his talk in Alpine, I recovered exactly the same thing.
You know,
When he bugged me about this by email a few days
yeah,
ago,
suddenly you all become smart. He became smart after he attended my talk at Elba. He said, "Of course, I should have remembered this before," and so on. Everybody of us is smart a posteriori. So I agree with you. But first, what I'm telling, it was in.
Can I make one comment? I think it's not a matter of being smart. I think he was definitely the first to realize that the effect was significant. So I think.
they derived the Lisa transfer function originally.
Okay, so my publication 1974. If somebody can present a publication before 1974, I will agree that it should be analyzed.
This work in Walquist is 1973.
Let me see. I'm quoting Frank, definitely. I know him very well. So I see a reference to Estabrook-Walquist, General Relativity, 1975, sorry. General Relativity and Gravitation, 1975. Grishchuk, Journal of Experimental Theoretical Physics, 1974.
Just to speak up for Frank, he's got it to all orders.
Yes,
He's got the answer to all orders in L over L.
Okay, very good. So what I want also to mention is the following. You know, the full truth is not only the distance. Distance is a single number. I'm sending light, depending on my definition of distance, by the way, and I am receiving back. And if the distance is the only thing I am interested in, then possibly it would be enough to do this calculation with a reflected photon. If you want to see the entire picture, if you want to understand the physics, if you want to prepare yourself for some possible applications, it is better to know what is going on in detail. So it may be in your local frame, but it is how you are becoming a physicist. You are now testing your intuition. I will be proposing to measure this actually as a magnetic prediction of general relativity. So I see this prediction at the level of magnetic analogy. If it was simply a distance, it would be a limited knowledge, I believe. It would be possibly sufficient for response function, but I think that I personally would not be satisfied. I wanted to see this, how it looks in, how it works in detail. So let's come to the response function of two-arm interferometer. What is important? Now you have two arms, you have calculation of a distance in one arm minus another one, and now green, it is a typical kind of response function. So green line is what you would expect on this electric component. But if you take everything into account, then you see that there is 10% in this example, or 5% correction, both in amplitude and in phase. How serious can it be? We now calculate the angular pattern for a fixed polarization. In this particular case, it is a circularly polarized wave. And now we are becoming physicists again, because...
You're looking at the detector beam pattern.
Oh, yes, yes, it is angular pattern of a detector rather than radiation. Yes, that's right. So the meaning of this figure, of course, that if you have a set of identical sources, which you know where they're placed, how they emit, and so on, and you're asking how your instrument reacts, then this length gives you the proportionality factor. So in some directions it will be 0, in some directions it will be 1. What is more important, definitely it is symmetric with respect to this axis. So if you have a source here or there, it seems to give the same response function. Now, if you take into account this magnetic component, then it is being deformed, and therefore, say, in this direction, your response is not the same as here. So you may either misevaluate the strength of your source or be blaming your instrument and trying to make it symmetric, whereas it was perfectly working instrument. It is simply how it reacts to the wave.
So I think it's important. So that's for a circular polarization.
It is for circular polarization.
And for linear polarization, I don't think the shape changes.
For linear polarization, it still changes.
It rotates a little bit.
It still changes, but in a different aspect. Let me possibly, since this question, can I write here? Is it all right? So for linear polarization, the delta D factor, which we are plotting actually here, will be LH, say, plus, if you are considering plus polarization, square root of some normal angular pattern function which we call electric and which we know, plus KL, our factor that we are discussing, times F plus H, and this is square, and this is square. So H means it is magnetic part, and E means that it is electric part, times sine omega t plus psi plus delta psi. So there is definitely shift in phase. Now, with respect to amplitude, in most directions where you can say that this term is dominant, then the amplitude response is the same as before. You are simply neglecting this term.
KL squared.
Huh?
KL.
Yes, you are right, Kip. It is KL squared. Yeah. But for some directions, and actually at this diagram, it is for directions where it looks like developing zero. Now it will not be zero. It will be determined by this term, because you are dropping this term, you are taking square root of this, you have more complicated angular dependence, and you have a small factor KL.
What I think happens is the pattern just rotates.
It is probably true. It is probably true, but it is rotating, not keeping the figure symmetric. It simply says that zero now in a different direction, but it is still deformed. It is not a rigid rotation of the entire figure. Would be dangerous in any case, but it is more than that. It is deformed, but in such a manner that I can neglect this amplitude correction almost everywhere except of some limited directions.
What is the value of KL on the figure?
It should be written in paper. I think that for illustration it is exaggerated. So for illustration it was taking something like 0.1, but in reality maybe it will be a little bit smaller. So
for LIGO at a kilohertz, which is the highest frequency
yes.
we're going to operate,
Yeah.
what is KL?
This is what I said before. KL is equal to 8%, 8 over 100, at 1,000 hertz. So whenever we are going to higher frequencies, it is even worse. And moreover, which we will discuss in a moment, it is amplitude of the correction. What I worry about, and still we do not know the answer, but maybe we will know tomorrow or day after tomorrow, how all that will be possibly worsened if we try to observe for a long time, or a source going through all these patterns, or if you take into account frequency dependence, because so far we are giving for a given frequency, and there is frequency dependence. So if source goes through the frequencies, at smaller frequencies, at a smaller correction, but then we have to integrate.
So that's without 4 kilometers?
Sorry?
That's So what, you need to multiply by the finesse, or doesn't that
No,
play into
the
it?
transfer function of the many bounces of the drop stars.
Yeah.
So this is astrophysical example where we will gauge the importance of these terms. And therefore, imagine that you have a pair of stars on circular orbit.
Let me just remark, from the point of view of discussing this in a local inertial frame, the correction, the normal analysis, the force that you get is proportional to the tidal field, which is Rj0, K0, or it's the double gradient of the Newtonian potential using a Newtonian term. The correction is just the next derivative, so it's proportional to the gradient of the tidal field or the gradient of the Riemann tensor times times L, the length of the car. So that's why it doesn't the bounces don't matter, but you're not reaching out and feeling the fact that the Riemann tensor is changing as you go on out, roughly speaking.
So what are we doing wrong? Well, if you are serious about astrophysics, and I'm serious about astrophysics, then I think that 10% is a huge correction in cosmology. 10% would change my cosmological parameters to the extent that they would be non-recognizable. So if cosmologists are caring about 5–10%, we representatives of exact science, I think we should be even more concerned.